Okay, thank you. So you may find some overlap with what said Benoit just before, but I mean, for those who have been sleeping, it should be a nice reminder. So, well, you all know the broad picture of star formation. You have a dense core in the interstellar medium that collapses under its own gravity to form a protostar and a protoplanetary disk around, and that turn into a stellar system with a star and maybe planets. The thing is that during this process, the angular momentum is not conserved. The angular momentum, total angular momentum drops by almost 3 orders of magnitude. So it's not most of the angular momentum is removed from the gas and material during star formation. So we can explain that with magnetic fields. So one of the process that remove angular momentum is the magnetic braking. So let's imagine some magnetic field trading some gas, some rotating gas. The motion of the gas will deform the magnetic field lines, but the magnetic field lines will resist this deformation and provide a counter strength, a counter force, counter acceleration that slows the rotation. Yeah, that slows the rotation here, and so the angular momentum is removed from the gas. And another phenomenon are magnetic outflows. So where the centrifugal force coupled with the magnetic forces to eject some gas with large angular momentum. So that's two phenomena to remove angular momentum during star formation. So these two processes need magnetic fields, and so to model them and study them, we need to use the framework of magneto-hydrodynamics, so MHD, which is just fluid dynamics with magnetic fields. And so the first studies used ideal MHD, which assume a perfect coupling between gas and magnetic fields, because it's the simplest way to model that. And we found that indeed increasing the magnetic field strength could increase the magnetic braking and remove more and more angular momentum from the gas. The problem is that for magnetic fields strengths consistent with what we observe in the interstellar medium, the disk that we could form were either non-existent or very, very small, which is inconsistent with what we observe. That's why we need non-ideal MHD. So as was explained by Benoit, non-ideal MHD effect weaken and change the magnetic braking, they weaken the magnetic field and allow the formation of disks with size that are coherent with what we observe. So that was half of the talk of Benoit just before. Yeah. So what is non-ideal MHD? Where does it come from? So you have the three effects that Benoit mentioned just before, the ohmic diffusion, Hall effect, and ambipolar diffusion, that each represent the decoupling of electrons and magnetic fields, ions and magnetic fields, and neutrals and magnetic field. And these effects, they weaken or alter the magnetic field strength and topology, and so the magnetic braking. So nowadays, in 2022, we know how to calculate those effects, to implement them, and we have a robust numerical method, this robust numerical scheme to include them in calculations, in simulations. That was a lot of work during the last 15 years or so. The main problem is calculating the resistivities. So the resistivities define the strengths of each of those non-ideal MHD effects. And the resistivities, they arise from the microphysics interaction between the particles in the gas. So the ions, electrons, neutrals, and the grains. So for example, the neutral particles, they don't feel the magnetic field, and so they can get in the way of the ions that want to follow the magnetic forces. And so well, the ions cannot move freely along the magnetic fields, and that creates a resistive effect. Another thing is that electrons can recombine with ions or can be absorbed by grains. So we have to account for all those interactions to calculate the resistivities. And so, for example, so for the ions and neutrals, we need to know their number, so their abundance, their mass, so their species, And same for the electrons. We need to know how many are there in the gas and at what rate they recombine with different species. So this is like doing chemistry, basically. And the grains. So the grains are a different problem because we need to know their size, their number, how many grains are there per size. Do they carry charge? If they carry charge, how many do they carry? And one fundamental thing we need to know about the grains to calculate all that is the grain size distribution. And something that we know is that the grains grow during the protostellar collapse. So here you have a figure by Guillet et al. So that's one reference for Emmanuel, who studied the grain growth during the protostellar collapse. So starting with an MRN distribution, so some micron for dense core typical densities, going to the brink of disk formation. The grains grow by coagulation by 2 orders of magnitude, more than 2 orders of magnitude. So grain coagulation is simply grains colliding with each other, sticking to each other, and so growing in size. And so this is something extremely important because the grain size is extremely important for the chemistry. I don't teach you anything there. For the ionization with an impact on the resistivities, and for their radiative transfer properties, the cooling with implication for the observations, of course, and for planets formation. So we need to account for the grain coagulation, the grain growth during the protostellar collapse. The problem is that grain coagulation is computationally expensive. They can, in 3D MHD simulations, they can slow the simulation by a factor 10 or 100, or sometimes even more. So here on the top left, you have the fundamental equation for coagulation, the Smolikowski equation that describes how each grain size interact with each other to collide and grow. And after some clever mathematical manipulation, we can arrive to this equation where you have the derivative of a grain quantity with respect to some variable named chi that is equal to something that's independent from the environment. So maybe that's a bit obscure said like that, but what this equation tells us is that the grain size distribution that coagulates is entirely determined by chi, that the coagulation process in this case is 1D. It's a 1D process and it's parameterized by chi. And chi is extremely simple to calculate. It's just an integral over some physical condition like the density, the temperature, some function of density, temperature, or it can be magnetic field as well. Another way to see this is that if you have exactly the same grains in different environments, very dense or very diffuse, they will coagulate at different speeds because they will collide at different rates, but the outcome of this coagulation will not change. It will always be the same. And so that's a powerful tool because the coagulated size distribution is entirely determined by the starting size distribution and the value of chi that is easy to calculate. So how to use this method? You can pre-calculate the coagulation of your size distribution as a function of chi, and you can tabulate it in a large file or whatever, and you can use the Shin-San code that does that. Then in your hydro simulation, 3D, 2D, 1D, or your analytical calculation, you calculate the value of chi, which is extremely easy, extremely fast. Then from this value of chi, you can read the size distribution from your table, and then you have a size distribution, and you can do whatever physics you want. Okay. So that's what I did using the Ramses code again, where I looked at simulation from the collapse of the dense core until the disk formation, where I used an initial MRN distribution that coagulates following this, it's a 1D process. So here is the evolution path of the MRN distribution by coagulation. you can see that, so this is the size distribution for several values of chi. And you can see that, well, the slope stays about the same for the size distribution, and the peak shifts to larger and larger radii. I have a dust-to-gas mass ratio of 1% everywhere. I calculate chi everywhere as a passive scalar, so in every cell. This is a very fast step. That's the only thing I need to do. So the coagulation has been pre-calculated, and I compute the resistivities, magnetic resistivities on the fly with the grain size distribution I can derive. So I won't go into the details on how I calculate those resistivities. I don't have time here. And here are the results. Here you have the peak of the size distribution as a function of density, and we have three zones that are clearly demarcated. Here, the envelope, in which the grains don't have time to collide enough to grow in 1/3 time scale. And so, well, they do not grow and stay sub-micron here with a peak of at 250 nanometers. Then you have the disk and pseudo-disk area where suddenly the grains grow quite fast to several tens of microns. And then the very center of the first hydrostatic core, in which grains grow up to 500 micrometers. And this is for a disk and the first core that are less than 1,000 years old. Means that in less than 1,000 years old, your grains grow from some micron to 500 microns. So if you're doing studies of protoplanetary disk, you need to account for the fact that your grains have already grown to those sizes. If we look at the distribution, spatial distribution of the grains, of the peak of the distribution, you can see that, well, without surprises, the larger size are concentrated in the larger densities area here in the mid-plane, John and Faison. We have like 100 or so AU radii in which grains are larger than 1 micron. And then the very center, the grains go beyond 10 microns. Now, what's the impact on the resistivities? Here you have the comparison of the resistivities for simulation with coagulation. So the one I showed before in solid lines and without coagulation in dashed lines. And in every case, the simulation with coagulation yields lower resistivities than without coagulation. And lower by several orders of magnitude. And we can have an idea of why it does that, how it works, because you have the coagulation, grains coagulate between each other. So small grains stick and form larger grains. So the surface area of the grains decreases because larger grains have smaller surface areas than the same mass of small grains. And so because you decrease your surface area of the grains, the ion and electron absorption by grains decreases. So ions and electrons are more free to flow however they want in the gas. And so the resistivities are lower. And this has a huge impact on the disk, because with coagulation, if you have lower resistivities, you have a higher magnetic braking, and so you form smaller disks. But without coagulation, if you have high resistivities, you have a lower magnetic braking, and so a larger disk. And well, if you have just one thing to remember from this talk, that I'm not saying that if you observe small disk, it means that you have coagulation. And if you observe large disk, it means you don't have coagulation. No, we know that we have coagulation. We know that the grains grow during the protostellar terms. My main message here is that the grains grow during protostellar collapse, and it has macroscopic effects on the disk. And I don't show it here, but also on the outflow. And so here are my conclusions. That's what's written. Well, the summary of my talk that was written on the right. Thank you.